All right, in this video, we're going to look at the squeeze theorem. This is also known as the sandwich theorem. So up first, let's look at how you would use a theorem. So I know that you were first introduced to theorems back in geometry. So I don't know how your geometry teacher taught you how to use a theorem, but there's a very specific way that we want to go about using theorems in calculus. So here's the general form of a theorem. You're going to have an if-then statement. Whatever comes after the if, we're going to call that the hypothesis. And then usually you'll have a comma with then, and whatever comes after the then, that's called your conclusion. So what you're going to want to do is you want to first check to see is the hypothesis satisfied within your problem. If you think it is, then you want to just go ahead and show all the work to confirm that the hypothesis has actually been met. So the hypothesis might have several different stipulations that must be true. And you want to make sure that you just kind of go through and just tick all those off. And you want to show this work because, if it's a free response question, the reader is going to be assigning points specifically to those points. They're going to be looking to see, did you actually consider the hypothesis for that theorem? Then once you do that, you want to go ahead and apply the conclusion, and then this will usually give you your answer for the problem. Finally, this is also important. State the theorem that you just used. Just write it down. If you use the squeeze theorem, you want to say by the squeeze theorem next to your answer. This could actually lose you a point if you don't just state the theorem that you used. So here's the squeeze theorem. This says if h of x is less than or equal to f of x is less than or equal to g of x for all x in the open interval containing c, and if the limit of h of x is equal to L and the limit of g of x is equal to L, both of those are approaching c, then that means that the limit approaching that same value c of f of x is equal to L. Okay, so that's kind of wordy. So notice the hypothesis has two parts to it. There's this right here. That has to be true. It also has to be true for all x around c. And then there's this here. The limit is h of x is equal to L, and then the limit of g of x is equal to L. That's all the hypothesis stuff. And then the conclusion is here. The limit comes after the then. It's the limit of f of x is equal to L. So let's think about what's going on here. We have this inequality chain. H of x is the left here. That could be the smallest function. G of x is on the right of the inequality chain. That's the biggest function. F is in the middle. The other part of the hypothesis here is that the limit of h of x is equal to L. So h of x is your left part of that chain. That's the smallest function. So the smallest function's limit is equal to L, and then your limit for g of x, that's the biggest part of that chain. That's also equal to L. So we're showing that the limit for h of x is the same as the limit of g of x. We'll notice that the f of x is kind of sandwiched between those two. So what's happening is that since the limit of h and g are the same, it's sort of squeezing the limit of f to also be the same. So that's the conclusion here, that the limit of that middle function is also equal to L. So here we have two functions. You have y equals x squared and y equals negative x squared. So the y equals negative x squared, that's the smallest of the functions. So the way it's laid out, that would be the way it's laid out inside of the inequality chain, that would be your h of x. And then x squared is the biggest function. That would be the g of x inside of your inequality chain. And then you have this function in the middle, y equals x squared cosine of 1 over x squared. And notice that this function, the middle function there, it is bound completely by x squared and negative x squared. All right, so think about it. If we try to find the limit of x squared cosine of 1 over x squared directly as it approaches 0, well, the graph of it looks like it's 0, but if we wanted to do this without a graph, you would try direct substitution, and you'd get some form of 0, and then you'd be dividing by 0. This would be like an indeterminate type form. So you couldn't find the limit of this directly. But what you could do is notice that that middle function is bound by the upper and the lower functions, x squared and negative x squared. And the limit of both of these functions is 0. You could find that just doing direct substitution. Therefore, we could just assume that the limit of that middle function is also 0. And we would be using the squeeze theorem to say that. So here's an example of how we would use the squeeze theorem. Let's say that if 5 is less than or equal to f of x is less than or equal to x squared minus 4 for all x, we want to find the limit as x approaches 3 of f of x. All right, so we've got this inequality chain. That's given to us, it says for all x. So that's one part of the hypothesis already satisfied. It's just given to us, so we don't have to rewrite that. The second part here is we want to check the limits for the left and right hand parts of that inequality chain. So the left part would be the limit as x approaches, and whatever x is inside the limit that we're trying to solve for, that's the same value we have to use for these guys. So this is x approaches 3 of 5. So the limit of a constant is a constant, so that's just 5. And then I also want to check the limit for the right-hand part. X approaches 3 for x squared minus 4. So that would be 3 squared minus 4. 9 minus 4 is also 5. So these two limits are equal. So we can check that off. So we have confirmed that the hypothesis of the squeeze theorem holds for this problem. So now we can just use the conclusion. And that is that the limit, so I'm going to draw these 3 dots here. This just means therefore. The 3 dots means therefore. So if I'm using the conclusion of a theorem, I can just start off my answer by just saying therefore the limit as x approaches 3 of f of x, and that also has to be equal to L. My L here was 5. Remember the last step, the last step that I said to do up here. Finally state the theorem that you used. So you always want to make sure you're stating the theorem. So therefore the limit is x approaches 3 of f of x is equal to 5 by the squeeze theorem. And that would be your answer. Okay, so give this one a shot. This says that 4 minus x squared is less than or equal to g of x is less than or equal to 4 plus x squared for all x. Find the limit as x approaches 0 of g of x. So go ahead and pause the video and then try to figure this one out. Okay, so hopefully you got an answer. I'm just going to work this problem like I did the last problem. So I'm going to start off by noticing that the first part of the squeeze theorem has already been provided for us. We have this inequality chain. By the way, this is a pretty dead giveaway that if you see an inequality chain like this, that you're probably going to use the squeeze theorem for it. So we have that inequality chain. That's one part of the squeeze theorem hypothesis. And the other thing is that we have to check the limit as x is approaching whatever value you're approaching inside the answer. So we're looking for x is approaching 0. And the left function is 4 minus x squared. So that would be 4 minus 0 squared, which is 4. And then if I check the right part of that inequality chain, that limit would be 4 plus x squared, x is approaching 0, so direct substitution says 4 plus 0 squared. And that's also 4. So the limits are the same here. So now the hypothesis of the Squeeze theorem has been satisfied. So now I can just say that it follows, therefore, the limit of that middle function, g of x, is what they're calling it here, as x goes to 0, has to be equal to that same value of 4. And remember to state the theorem that you used, so it's by the Squeeze theorem.